What if I told you the laws of physics don't say warp drives are impossible? They just say they're ridiculously hard. In the world of science fiction, warp drives let you bend space, skip across galaxies, and make light speed look slow. But in real life, we're stuck crawling through the cosmos, bound by the universe's ultimate speed limit: light. 300,000 kilometers per second sounds fast, until you realize that even at that speed, it would take over 4 years just to reach the nearest star system, Alpha Centauri. That's not practical travel. That's a one-way mission, and you'd still be in the cosmic neighborhood. But what if we didn't have to move through space at all? What if we could move space around us? Enter the warp drive, a concept that doesn't just push against the rules of physics, it tries to outsmart them. Instead of accelerating through space, it bends space-time itself. In 1994, theoretical physicist Miguel Alcubierre proposed a wild solution to Einstein's field equations. His idea? A warp bubble. Inside that bubble, the ship stays completely still. It doesn't move. But the space behind it expands, and the space in front contracts, dragging the bubble forward and everything inside it. It's like surfing a wave of space-time. This isn't just a sci-fi trope. The equations are real. The math checks out. And while it's nowhere near being buildable, it cracked open the door to something bigger, faster than light travel, within the framework of general relativity. Of course, there's a catch, or several. Building a warp drive isn't just a question of technology. It's a question of energy, materials, and a lot of physics we don't fully understand yet. But the most important part? It's not impossible. And in science, not impossible is where everything begins. The warp drive begins with a loophole, one buried inside Einstein's own theory. General relativity doesn't just describe gravity, it describes how mass and energy curve the fabric of space and time. That curvature is what we feel as gravity. But here's the twist. If you can curve space-time one way, you can, in theory, curve it the other. The Alcubierre drive is built entirely on that idea. It uses a specific solution to Einstein's equations, the Alcubierre metric, to describe a bubble of flat space surrounded by curved space-time. This bubble moves not because the ship accelerates, but because space-time itself shifts. It's the ultimate cosmic cheat code. From inside the bubble, the ship doesn't feel any acceleration. There's no stress, no g-forces. It's perfectly still. But to an outside observer, that bubble, and everything in it, can move faster than light. Why? Because space-time isn't limited by the speed of light. That limit only applies to objects in space, not space itself. Now here's where things get strange. The Alcubierre drive requires an energy source unlike anything we've ever created. It needs negative energy. Not just a shortage of energy, but energy with the opposite effect on space-time. It's the kind of energy that would repel rather than attract. And no, this isn't antimatter. This is exotic matter. There's only one place in physics where negative energy shows up: quantum field effects. One example is the Casimir effect, a measurable force between two plates in a vacuum, caused by suppressed quantum fluctuations. It's real, but the amount is so tiny it's only useful in lab-scale experiments. To build a warp bubble large enough to fit a spacecraft? Early estimates suggested you'd need negative energy equivalent to the mass of the Sun. Later models reduced that number to about the mass of Jupiter or several Earths. Still beyond imagination. And this assumes you could even generate or contain exotic matter, which we currently can't. But recent studies have pushed the idea further. In 2021, physicist Lentz proposed a version of the warp drive that works with positive energy only. If true, it sidesteps the exotic matter problem, but at a cost: massive energy requirements and even more complex space-time geometries. How much energy are we talking? In some models, the amount of power needed rivals the total output of an entire star. To build and maintain the bubble would require tapping into something like a Dyson sphere, a theoretical megastructure that surrounds a star to capture all its energy. Still, compared to impossible, colossally difficult is progress. So, How fast could a warp drive go? In theory, there's no limit. Since space is what's moving, you could cross 100 light years in a matter of weeks. Want to reach another galaxy? You might get there in a lifetime, or less. But every increase in speed requires exponentially more energy, and the faster the bubble moves, the more extreme the space-time distortion becomes. There's also the risk of catastrophic energy buildup at the front of the bubble, a death ray effect theorized by some physicists, where high-energy particles collect and release at arrival. And let's not forget time. Would time slow down for the passengers? Would they return home and find centuries have passed? That depends entirely on how the bubble is generated and how time behaves inside it, a question no one can answer yet. Despite the obstacles, some scientists are exploring the fringes of the idea. NASA's EagleWorks lab, once led by Harold "Sonny" White, has tested concepts related to warp fields. In 2021, a team working with White claimed to have observed a nanoscale structure that resembled a warp bubble geometry, a kind of experimental blip that suggests these ideas might one day leave the whiteboard. We are nowhere near building a real warp drive, but the math is real. The physics doesn't forbid it, and that's more than we can say for most science fiction. So what does all this mean? It means warp drives are no longer just fantasy. They're on the outer edge of scientific possibility. The math is solid. The physics is stretching but not broken. The technology? Still a distant dream. But science doesn't leap forward with certainty. It crawls forward with maybe. And that maybe is what takes us from heavier-than-air flight to jet engines, from rockets to the moon, from dial-up internet to artificial intelligence. All of it seemed impossible, until it wasn't. Warp drives challenge our understanding of reality. They force us to rethink space, time, and what speed even means. They ask us to imagine a future where stars aren't just pinpricks in the night sky, but real places, reachable within a human lifetime. We may never build one, or we might build one in 100 years and laugh at how primitive we once were. But the first step is already happening. Scientists daring to ask what if, and physics not slamming the door shut. In a universe this vast, that alone is worth exploring.